that as an opportunity to also think about this problem and try to have better intuition of like how to attack this problem. So I think the first part of the talk, maybe most part of the talk, is going to be just about that in general. And then if we have time, I'm going to cover our recent work with Sanjeev and Rong and Yi. So please stop me whenever something is not clear or you have questions. We don't need to go through everything in the PowerPoint. So, okay, you have all heard about AI, deep learning, neural networks. These days, these things usually respond to the same thing. I think it's a hype, but it also does interesting stuff. For example, AI can beat us in Atari games. It can beat us in game of Go. It beats us in poker. It can do better than certified dermatologists in detecting skin cancer and classifying it. It can also learn to write characters and read characters by a few examples. Driving cars, generating faces that look very familiar and you can't tell the difference from the actual human face. Generating art, being creative. And more recently, we have also observed that other sciences have started to use these technologies to understand. So if a problem is so hard that human cannot understand it, maybe we can use AI to understand something about the problem. So these are all exciting, and it creates a great opportunity to contribute. And all these different applications seem like, they all seem very different, but it all started from a very simple application called classification task. So let me tell you what is this task. You have a data set of, let's say, images, and you have 10 classes, and you want to classify these images to one of these 10 classes. And the way it works is that you're given an input, which is an image, and then you're giving this input to some black box function, and this function is going to give you some scores. That these scores are real numbers, and it's going to tell you which class is more likely based on this function guess. And we're going to pick the one with maximum score as the correct label and predict it. So here, for example, horse has the highest score, so we're going to predict that the label is horse. For example, this function f can be just a linear classifier. In that case, the dimension of this weight matrix is just input dimension times 10, which is number of classes, right? So you learn a linear combination of features that predicts score for each label. And also, we should have a loss that, given the correct label tells and the output score of the function, it returns a number that tells you how good is the prediction, right? And now, the task of classification is to learn these parameters in such a way that you predict things correctly on the training set and set of data that you have, and you hope that you're going to also do well on prediction time. Now, to be a little bit more specific, because we want to study this problem, let me tell you a little bit about the learning framework. So again, we assume that we have inputs and labels, and we assume that these inputs and labels are coming from some unknown distribution. So this is one assumption, and we don't have access to this distribution, but we have access to a training set of samples that are generated from the same distribution. And the goal is to find a predictor that with minimum expected error on the distribution. Of course, since we don't have access to distribution, so we minimize the error on the training set and we hope for the best. This error on the expected error, we call it test error. Now, it's easy to see that you can decompose test error to the training error, which is error on the training set, plus the gap between error on the test error and error on the test set and error on the training set. And we call this gap the generalization error. Now, given any fixed function that's chosen in advance before seeing data, it's not hard to see that the generalization error is not going to be large. You only need a few samples using large numbers to make sure that the test error is not very different from the training error. So a few samples is going to be good enough. But the problem is that if you choose the function f in advance, then you're going to have high test error, probably like something like random. Random is the best you can get. But what can we do is that we can pick a class of functions in advance. And now we can apply the law of large numbers on this class, make sure that this generalization error is small for every function in this class. And now that we know this generalization error is small for all functions in the class, we can pick the one with minimum training error. So this gives us some generalization bound like this, which says training error is test error is bounded by training error plus some term that corresponds to the size of this function class divided by number of samples on the training set. So the size of the function class contributes logarithmically to the generalization error. And then there's this trade-off. If you increase the size of the function class, of course you have more rich class, and the training error goes down because you have more choices, you can feed the data better, but the generalization error goes up. And we have to find the right balance. So one might say that just counting number of functions is sort of stupid. We want to be better than that. We want to actually count how many behaviors we observe, how many different functions. If two functions are really similar and approximate each other, I don't want to count them twice. So whatever notion you come up with, we can call it capacity, something that captures how many different behaviors we observe. And capacity roughly corresponds to also one other way to look at it is capacity is the number of samples we need to generalize. Because if capacity is, this term is more than m, then it's going to be greater than 1 and it's pointless. So capacity for us is the number of samples you need to generalize for a function class. We all have actually very good intuition about capacity. So if I give you this linear separator and ask you whether it's a good linear separator, you don't have enough information to tell me if this is good enough. How about now? Still not good enough, right? Now it seems more reasonable, and I'm personally convinced that this is actually not bad. But how about this one? So you need much more evidence for this one to be convinced that it's generalizing. So what we did in our mind is that the moment you saw this, you assigned this to a class of linear functions. You had some approximation of how many behaviors you can expect from linear function, and then you had some expectation of number of samples you need to be convinced that it's going to generalize. For this one, the approximate number was larger, so you needed more evidence to be convinced that it's going to generalize. And this is the rough intuition about capacity. Whenever we talk about capacity, it means how complicated is the class or how many samples you need to generalize. Okay, so we talked about learning. So since we want to study deep learning, we should also talk about what deep learning means. So there's a discussion what deep learning means, but I think deep learning is about composition of differentiable parameterized functions. So the composition is important. They are differentiable, they are parameterized, and they have many parameters. So for example, here you see a simple 3-layer LSTM model. It has many components. And if you open up each component, it has several other components inside it. Some of them have parameters, some of them don't have parameters. So at least to me, this seems like overwhelming and complicated. If I want to study such a thing, I would just rather not study this. Just stop. So what should we do with these models? The approach we take is usually simplify the model. But we have to make sure that when we simplify it, we don't lose the actual property that we care about. So this is very important. We have to understand the model good enough so that in the process of simplifying it, we shouldn't lose the main property that we want to study. For this case, for generalization, there are again debates. Some people might say that some model is too simplified or less simplified. But I think feed-forward networks are simple enough, and they can capture the properties we observe in deep learning models. So I'm going to focus on a special case of them, which is fully connected networks. And I'm going to tell you what's a fully connected network. So given a data point x, which is d-dimensional, you can think of multiplying it by matrix V. So just a linear transformation. And now this gives us values that for a vector that we call hidden units, and in the hidden units, we just zero out the negatives, okay? So all the negative values are going to be 0 as the output of the hidden unit. And then I'm going to multiply another matrix by the output of the hidden unit, and this is going to be the output of a 2-layer network. Now, if I have more layers, I repeat this process more times. But this is roughly a fully connected network. As you see, it's a very simple process to calculate the output. And it's not hard to see that this is actually a piecewise linear function, right? Because of this nonlinearity that we call it ReLU, it becomes piecewise linear.
By fully connected, what do you mean precisely?
So
the V is not fully.
So fully connected means between, so we have layers, and between layers, every hidden unit is connected from the previous layer is connected to every hidden unit
So
in the next layer.
in your picture.
Why? What's
That's not true.
You did not draw the full bipartite graph, but the tree is not sparse necessarily, that's all.
So
Oh yeah. This one is missing. Yeah, I saw it. Yeah, you're right. But every input is connected. So sure. Okay, now that we have this fully connected network, we can fix architecture. Let's say I fix depth and I fix number of hidden units. Let's assume that for simplicity that every hidden layer has the same number of hidden units. So we just need to pick number of hidden units and depth, 2 parameters. And when we fix that, we have a hypothesis class, which is class of neural nets with fixed depth and fixed number of hidden units. And now we have to just play with parameters, and each parameter gives us a different function in this class. And we want to study this. And there are 3 questions that we always ask when we want to study learning about each hypothesis class. And that's expressive power, optimization, and generalization. Expressive power, roughly speaking, corresponds to what is the best function in the class that approximates my desired function. So you can think of it as what's the best training error I could potentially get from functions in class F. Optimization is about, can I actually find that efficiently, right? So that's optimization. And the third one, generalization, is concerning about the generalization error. So the first 2 are about training error, and the third one is about generalization error. So what we know about this class is that, okay, if it's large enough, if you have enough hidden units, if the depth is good, then you're going to have a great expressive power. We are not really concerned about expressive power of neural networks.
Well, when you say we know this for a bunch of things that exist in, that were successful so far.
Exactly.
Yeah.
Yeah, so for feed-forward networks, we know we have like different theorems showing that based on approximation, you can increase the size, and it gives you a reasonable.
But this is only for some function.
For continuous function.
Every continuous.
For every continuous function, but it could be exponentially large. So it's not polynomial or. But when we go to optimization, what we know is that even if the number of hidden units is logarithmic in the dimension of input data, there's no polynomial time algorithm that always works, which is disappointing. And when we go to capacity and generalization, based on the parameters we have, we know that depth times number of weights roughly captures the generalization, which is again disappointing because like when we want to have enough expressive power to capture the data, then the generalization is going to be too large, so we need too many samples. So this is what like classical study of neural networks would tell us. This is the old works, classical study of neural networks. So now let's forget about theory for a few minutes and do some experiments. So this is the one we want to study, but I'm hoping that we see some connections between all these 3 when we talk about generalization. So we're going to do some experiments on MNIST dataset, which is just handwritten digit classification. We are given 60,000 images of each of them correspond to a different digit, and we want to classify the right digit. So we use this the same 2-layer network that I described to classify this. And the training process, we just use a stochastic gradient descent We initialize weights from randomly from Gaussian, and then we just optimize using gradient descent, okay? And now I want to see, so we discussed that how the size of the network affects the generalization and optimization, and now we want to test that, right? There are two ways to test this theory about the size. One is increasing the width of the network, another is increasing the depth of the network. So for now, we're going to just look at increasing the width of the network, which is number of hidden units, and later we're going to see some observations about the depth.
How do you pick the 0.01?
This is just because I didn't want to use notation, but this is like number that people use in practice and usually.
It's a magic number? Or
Yeah, somehow it happens to be a magic number, yeah. It works most of the time, so. So what I want to do is that I want to train networks of different sizes with different number of hidden units, and I want to see how the optimization behaves and how the generalization behaves. So the theory tells us if you have more hidden units, you're not going to be able to optimize, and you're not going to be able to generalize. So this plot shows a training and test error for different networks. Each of these networks has different size. Each of them I initialize randomly. I do the optimization, and I measure to the convergence, and I measure the training error and test error, okay? So this is for smaller sizes, everything makes sense. So you observe that when I increase the size of these networks, I have a larger hypothesis class, so I get better training error because I can feed this data much better. And I also get better test error because test error can be decomposed to generalization error plus training error. And you can see the generalization, which is the gap, is increasing. So I have larger hypothesis class, and that's why I have more generalization. And everything seems to make sense. So what do we expect after this? So a network of size 64, which is 64 hidden units, is enough to feed the data completely. So if I use a larger network, it's not going to give me more expressive power because 64 was enough. So first question is whether I can still get zero training error for larger networks, because the theory tells me that like even logarithmic in size is too much. So that's the first question. Second question is what's going to be the generalization? So we expect, so I'm going to tell you about the training error first. The training error is going to be 0 no matter what's the size. This is one observation which contradicts what we had. And for generalization, we expect to see something like this, right? The generalization error should increase for larger networks. But what?
When you say convergence, did you train until training loss convergence or test loss convergence?
Training loss. Test loss we don't check, right? Until we converge.
But test loss does not converge yet when training loss converges. Test loss
that
keeps
wasn't
evolving.
Yeah, so training process, you stop whenever you converge to 0.
It doesn't do anything.
So you converge to 0 and you stop. You don't move when you stop, right?
I'm saying that empirically, if you keep training, that you will see that the test loss will continue changing.
Yes.
Even though the training loss.
But if the training loss is 0, you're not going to move because you're doing local search.
Okay. Well,
So if it's exactly 0.
it's still stochastic. There's still some noise there.
No, if you reach the 0, even though it's a stochastic, it means it's 0 for every data point. So you're not going to move. There is some tricky stuff here, so I don't want to go to detail, but we can discuss after. So what we observe is that the generalization error actually improves for larger networks. So what's going on here? I have a larger hypothesis class. I'm not doing any regularization, no dropout, no regularization. And I'm continuing until convergence, and I get better and better generalization error. It plateaus toward the end, but it's surprising that you see a significant improvement at the beginning, and it's not going up. It doesn't. Actually, I tried these experiments later with like even larger number of hidden units. Already 4K hidden units means that this number of parameters is roughly 4 million, and the number of the data point we have is 60,000, and you're not overfitting. So what's going on here? So there are two things that we are not taking into account. One is that we are doing these experiments on real data, right? This is not worst case distribution. This is distribution on real data. Another thing that we are actually using a very specific optimization algorithm to find this hypothesis. I called it local search because I tried like some other algorithms like gradient descent, conjugate gradients. They all gave me similar behavior. So I'm assuming there's something about local search. So I'm going to go back. Okay, so before that, so let's talk about real data and doing local search on real data. So real data determines the surface of loss function. And this limits what you can reach by doing local search. So if I start here and I do local search, there's no way I end up here because it's just going to go down and get stuck somewhere, right? It has many global optima, and it just finds the one that's the closest or around it. It's not going to end up here. So if I start like roughly in the same area, if my initialization is roughly like around this area, I'm not going to go outside of this. So effectively, that means that my hypothesis class, which is the function that I'm going to end up with and I'm going to choose, is much smaller than the original hypothesis class. And that could be the reason we are getting generalization. Actually, when I was looking at this picture, it was interesting. I was looking for something that captures this intuition, and I had a hard time finding it in computer science literature or like in websites. But I found very interesting pictures in chemistry, physics, like energy landscapes, and it kind of, I don't know, it seems somehow related, the property that we observe about the landscape of loss functions.
This landscape is data dependent. This landscape is data dependent, right?
Yeah,
you look at the empirical
exactly. Exactly.
So it's like you say that you're going to look in a small surrounding, but that small surrounding is already data dependent, so it's not exactly that. The hole where you search is depends on your. It
depends on the data, but what if all real distributions have something in common? Then you can say that it's not dependent to the specific task that I'm studying. It's some property of real data. So if
no, I'm saying if the landscape you're optimizing over doesn't depend on your data, right? Of course, the landscape is data dependent.
Yeah, but
it's true. You search in an environment. It's like saying that the optimum is a single optimum.
No. So what I'm saying is that there's some property of real data that's general and shared in all tasks. Then that would make sure that even if your task is different, even though your task is different, even though the landscape is different, it has some similarity in the structure to other landscapes. So it's not really dependent on the distribution that you care about, but your distribution has something in common with other distributions. And if we can capture it, then we can say that we are effectively like limiting the size of the hypothesis class by understanding this structure in distributions of real data.
Do you test, do you have a way to test even the functions that you come up with in this optimization, how different they are from each other? They are probably extremely different. From what viewpoint? Locally optimal solutions that you find in
if you do
subsequent runs.
Oh, yeah. So it's an interesting question. It depends on how you compare them. If you compare them in parameter space, they look very different, individual parameters. But so one way to compare them in the function space to see if they're actually different functions is, for example, generating random noise, feeding in the random noise to the function, and just comparing the outputs of these two functions, right? That gives you some sort of notion that how different are these two functions. If you do that, you see that they are not really different. So it points to this hypothesis that you converge to around the same points, even though so one way to think about this is that even though you're you're doing random initialization, so if you look at each hidden unit, it's sum over random points.
You're saying
right?
In some other parameter space, the energy surface does not look like this, but it looks more like a convex function. Because all these local optima, even though they are different, and you can get to each and every one of them.
Not if you initialize in this area. So let's say all the landscapes are different, but they share some big area with big flat local minimum. right? Not in the parameter space, in the function space.
This seems to be one explanation. Another explanation is that you may get to very different local minima, but they are somehow isomorphic.
That's okay. That's my way of saying they're the same. Like if they are isomorphic, like
there are two ways that they can be the same, right? They can be
yeah.
the same just on data that
exactly
be handwritten numbers, or they can be the same on random noise. And you're saying they're even the same on random noise.
I've just done one experiment on one structure, and that was telling me that they're like the same even on random noise. Like this experiment and feed forward. So this ones, I know they're the same even on random noise, like almost the same, not exactly, like numerically, which is surprising. But yeah, it could be that they are the same on, it could be this case that they are the same only on the data distribution, on the supportive data, not outside of that.
So when you say the same, the distribution for noise is just more or less uniform for?
It's like Gaussian noise. So you generate Gaussian noise, you feed in, and then you compare the output of the function.
And the output would just be that it doesn't know what it is? I mean,
it would be the same for, if you have two different runs, the output would be similar.
I'm asking what the output is for noise. It's just saying the same probability for all the 10 classes, more or less?
I don't remember this one, yeah. I don't.
And just one more thing, like this, I mean, this description makes it seem like it might be this property might depend on your initialization. Like morally it shouldn't, but it really makes it seem like it might. Right?
Yeah, but the question is, so the question is whether the initializations are really different. Like if you think about random initialization, so think about like a two-layer network, consider a two-layer network with many hidden units. If you randomly initialize the bottom layer, that actually corresponds to a kernel, a fixed kernel. So you can think of that as a very fixed initialization. Even though it's random, it's approximating a fixed kernel. So it could be that initializations are not actually very different, not in the whole network, but in the bottom layer of the network.
I meant not initializing with Gaussians anymore, like initializing one coordinate much larger than the other or something.
Yeah, if you do that, then the picture probably looks crazy. So if you initialize the way people initialize in practice, then you get this observation. If you initialize like literally randomly in the landscape, then I don't think you can even get the interesting result. You actually have evidences showing that there are very bad global optima that we never end up with. So that's also telling us that there's something about local search, that we never end up in those bad global optima.
I mean, there have to be, right? Like if you wanted to, you could train on the data set. You could train on the function that is correct for all training data.
Exactly.
Correct for all.
That's actually the experiment. Yeah, that's the experiment that shows. So you actually show that there exists a function that gets zero training error, but it has very bad test error. And you can literally find those functions. So suggestion is, instead of looking at that function on the top, we look at this modified version and try to understand this class. The class of functions, which is a subset of the one in the top, but the ones that can be reached by local search on real data. So we try to understand this, and then we have to answer all these questions again for this class. But how do we understand? This seems very difficult, like real data. What is real data? How can we even think about this class? So let's imagine for a second that we have a 2D structure, and this is the class of all functions that we converge using local search on real data. And it's very hard to capture. So what can we do about this? So we can try to find a complexity measure, some guess. You can guess that maybe neural nets with a small L2 norm of parameters can capture this. And now if I have this assumption, I can find this smallest alpha such that this class of neural nets with L2 norm bounded by alpha includes a class of neural networks that you learn on data. So you can measure L2 norm on all neural nets that you trained on real data, and then take the max, and that gives you a class that bounds this. This is like, let's say someone who has never looked at data guessed that L1 is the right measure, and it can capture this mystery about generalization, and it doesn't seem like that. But someone who has worked with data a little bit more might guess L2 is the right one, and the hope is that we actually find this measure eventually that's tight enough so that we can see that networks that we actually train have really low measure. And we can actually see that when you optimize these networks, you're actually converging to networks that have low measure. So if it's some weird norm, you should actually observe empirically that when you're optimizing, when you're doing gradient descent, you're improving this norm. And you should also observe that if you have a network that's not generalizing, it's going to have high norm. So then this measure is going to be good enough. If I have a measure that empirically correlates with generalization, and I can prove that networks with that low measure are going to generalize, then I'm going to be happy that I'm going to claim that that's the right measure. Not the right measure, but a right measure. So I also want to say a little bit about why we want to find this measure. So if we know this measure, then there are two directions that are really exciting. One is that you can actually use this to design better models. You can enforce this measure in your model design, or you can enforce it by optimization. Right now we are just doing local search and we end up somewhere that we don't know. If we actually know that we have a good measure, then we can actually regularize it and actually work this with this hypothesis class instead of starting from large hypothesis class and doing local search blindly without knowing where we are ending up. So that's the hope. Okay, so in more classical settings, people have tried to come up with other measures other than parameter counting. And the famous one is looking at the norms of parameters, as we discussed. So the intuition is that you don't need to actually count the number of parameters. The magnitude is more important than just the number of parameters. And we actually tried to come up with generalization, and we had a result showing that the capacity is independent, can be independent of number of hidden units, and can be expressed as norm. There are also older results by Bartlett, and there are new results, but this is more relevant for the feed-forward network that we studied, which says the capacity is bounded by just for product of Frobenius norm of the layers. And we were happy with it because...
the same result, what does it mean? I mean, this is under what assumption about the data? Is this
no assumption. This was still no assumption.
An arbitrary distribution that an arbitrary function that you are trying.
Yes. So you look at the class of neural networks with bounded norm, and then we bound the complexity of that class. This is without any assumption.
Oh, it's the complexity of the class. It doesn't mean it generalizes.
No, it generalizes. It's a generalization bound. So generalization bound. So when I say capacity, I had this bound that training error is bounded by, test error is bounded by training error plus this divided by m, square root of this thing divided by m. So this is the generalization error for any distribution. So this is still doesn't assume anything. Of course, if so that it captures the behavior of distribution in a specific way. If your distribution is really like worst case, then you're not going to be able to even fit it with a network with a small norm.
Exactly. So you're assuming something. I'm not.
So you're not assuming because you're going to get high training error. So if you're bound.
With large margin, if there is a solution with large margin, you will find it and everything is okay. If you cannot find it, then
you get high training error. So it's another way of like it's another way of saying you're assuming, but yeah. Okay, so we were happy with this because we didn't really check back if this was a good idea. And in a recent work, we checked different complexity measures and on the same experiments, and we were expecting this norm to go down, but this is what we observed. So it's still better than counting number of parameters, but it's actually the opposite of what we want, which is disappointing. And
this is for the digits?
yeah, same experiment, yeah.
And how many layers?
This is just one hidden layer.
Just one.
Yeah, you increase number of hidden units. And we looked at, I'm not showing other norms, we looked at all other complexity measures that have proofs, and none of them actually is the other way around. All of them are the same. So I'm going to stop here for widths. There's no answer. How can we, right now we don't know how to answer this question. And I'm going to go to the other direction, which is what about depth? How about if I increase depth? what do we know, and what are the current knowledge about this?
So you're just leaving this open.
This is open, yeah. Okay, so what we observe is that during the last few years, there has been lots of developments in networks that are deeper. We have technologies that allows us to train deeper networks, and we get better and better results. This is the result of ImageNet competition for classification. There are like 1,000 classes in this competition, and so in 2010 and 2011, there are shallow networks, and then you see that they eventually become deeper and deeper, and this is just until 2015, which they showed that you can train 152 layers and you get much better result. They actually showed later that you can even train 1,000 layers with the architecture that was suggested without losing accuracy. So the latest architectures we have allows us to train deeper and deeper models without losing anything in accuracy.
What are the numbers? These are the errors?
These are the errors, and human level accuracy is 5%. So like after 2014, these are already like beating human in the task. I should say that like humans are not really good in classifying 10,000 things. It's just too complicated.
When
But
you say shallow, is it the case that back in the day they were called deep? But now
I think so. I'm not sure. I'm not sure. I'm not sure about these. I don't even know what are these models. The shallowest I know, I even call this one shallow, but 8, like if you train 8 layers these days, it's not. So what we did is that we said, okay, let's look at the shallowest one that people call deep. And this is reasonable enough, like almost 20 layers. And so I'm almost going to the direction that I'm going to explain our recent work to Sanjeev. So we looked at this and we said, okay, let's measure how we are doing. So these are different generalization bounds that are suggested, older one from Bartlett and some recent ones. And I can tell you roughly what they correspond to. They usually, the capacity measured by these norms correspond to product of a norm across the layers. So if you have 10 layers, it would be product of Frobenius norm of the layers, or product of a spectral norm, or some other norm of the layers. All of them have this form. And if you have worked with neural network, you can already guess it's going to be catastrophic. The capacity that these models are suggesting are much worse than number of parameters. Number of parameters in this model is just 10 to the 7, and the best capacity we have is 10 to the 15. So we started this to get some understanding that's just better than parameter counting, and we are ending up with measures that are like exponentially worse. So what's the explanation? Why is this the case? Because all these models ignore anything about data. They ignore anything about local search. They don't actually look at the networks trained by SGD to see what properties they can use to get better bounds. Because these networks don't really work in like adversarially bad ways. So if you can find those properties, then there's hope that we can actually improve this capacity. Right now, like when we increase the weights, we are a little bit better than parameter counting. On depth, like the first step is to actually get to parameter counting, and then be able to improve upon that. So how can we?
Why are you taking the product of the norm? Why is it
so roughly,
naturally, just because like matrix multiplication and that's the norm of the product.
So roughly speaking, the generalization depends on the Lipschitz of the network, and if you don't make any assumption, the Lipschitz of the network can be as bad as product of norm of the layers. So if you have a what?
In reality, it's invariant. I can scale the net.
Yeah. So it's like, so actually if you use Frobenius norm, you better balance the layers, because that would minimize the Frobenius norm, and then that corresponds to product of the norms instead of sum of the norms. Okay, so this is what we have, and the question is whether we can use actual properties of networks trained on real data to get a bound that's not much, but just better than VC dimension bounds.
Behnam? So
Yes.
why do you say that these bounds do not capture the true network? Because aren't you at the end of the day looking at the bounds, let's say the Frobenius term of U and V of the trained network?
Yes.
So
These are the trained network. These numbers are for the trained network.
yeah, so why do you say that they do not capture the data itself?
So these bounds are suggesting that I need 10 to the 15 data points to generalize, right?
No question.
Yeah.
But, okay, that's the other thing. But,
Yeah, but also empirically, like if you actually like train use different optimization methods and then measure all these bounds and then ask these bounds to tell you which one is going to generalize better, they're not going to be able to tell you. So hard tasks like the ones I showed you, they all fail in tasks that actually captures how good they are. So we want both of them. We want to be tight and we want to be able to capture things empirically. Okay, so let me go back a little bit to like general intuitions. When people talk about generalization, there are like different ideas floating around that are like general, just to give a sense. One is flat minima that was discussed in 90s and then recently brought to attention by Keskar et al. And that says like if you have a flat minimum, that means that you're going to generalize. And so the intuition, one way to think about it is just, let's say this is your hypothesis class, and this is a flat minimum, which means all functions in this area are roughly the same. That means that you can actually count how many of these areas you can have, and that gives you number of bits you need to describe this hypothesis class, right? Because all of these are the same. So if you have a flat minima with large volume, that means that you're going to generalize because the number of these areas are going to be limited. That's the general intuition. There are also other intuitions that actually correspond to the same thing. One is noise stability, which says if you perturb parameters and the loss function is not changing, then you're going to generalize. This is also very similar to flat minimum, because if you have flat minimum, perturbation are not going to change the loss function. And instead of volume, then you have to deal with KL, the divergence of the probability that you perturb parameters. So these two are roughly the same. There's also recent work showing noise stability with respect to the input of the layers, which means if you perturb output of the neurons, output of the hidden units, the output of the network is not going to change. This is like somehow a little bit different than noise stability of parameters. That says this is noise stable with respect to the input of each layer separately.
How do you know if a function has a flat minimum?
So as I said, these are like very vague descriptions. So flat minimum, you have to actually first define how do you measure the volume. Like, are you using L2 norm? Like, how do you measure this volume? If you measure it, then you can bound the generalization. But if your question is how do you empirically tell flat minimum, empirically the easiest thing is through noise stability. You generate Gaussian noise and you measure the output, and it gives you like some expected flatness instead of worst case flatness. Okay, this also connects to something. Okay, so noise stability, we can actually check. So the last one, adding noise to layers. We check this. We add noise to outputs of one layer, and we check how this noise is going to propagate to the output. We want to know if networks that are trained on real data actually have this property, right? And this is what we observe. We actually observe that when you inject noise, even though the magnitude of the noise we inject is really high, the noise suddenly disappears after a few layers. It's like the noise wasn't there. And this is really interesting. It means that the neural nets are really resistant to the noise added to each layer. And this was already also observed, like if you ask practitioners, they say, of course, we already knew this from many years ago. And there are like different regularization to make this actually even better. But this property is promising because it tells us that these networks are resilient with respect to noise. And this
You re-optimize? Or
no, you just,
yeah. This is the optimal function.
Exactly.
And then you apply noise.
Yeah. This connects to reliable machines from unreliable components. Von Neumann has talked about circuits with components with that are noisy, and you want to design circuits that are going to be resilient to this type of noise. And I actually, it was interesting to me that I read a note from Shannon talking about von Neumann's contribution, and there's a paragraph says reliable machines and unreliable components. Shannon says we have in human animal brains examples of very large and relatively reliable systems constructed from individual components, the neurons, which would appear to be anything but reliable. And then he mentions later that in communication theory this can be done by properly introduced redundancy. So redundancy is overparametrization, right? Overparametrization is introducing extra redundancy, and redundancy allows us to have error correcting codes, so overparametrization should be able to allow us error correcting. So can we capture this by compression? If you have larger code that's error correcting, there should be a way of compressing it. So let's compress neural networks. If I have a network and I can compress it to another network with much less number of parameters, which approximate the original network, then I can just count number of parameters on the second network and say this is the generalization I get, right? Okay, so in order to compress it, I can just start layer by layer. So if I can show you that compressing one layer is not going to change the network, then you can apply induction and say that this is going to be true for all layers. So all I need to do is just compress one layer of the network, and then hopefully using the property I showed you, the noise that's added by the compression is not going to be large, and when you propagate it to a network, it's going to disappear, right? Okay, so this is the, sorry. So this is the compression algorithm. It's very simple. I shouldn't actually call it compression, but I'm going to explain you a little bit more. You generate k different random sign matrices, and now you're just going to calculate inner product of your weight matrix with the sign matrices, and you're going to need to store these parts as parameters. These are just one. So you have k numbers as parameters, and these random matrices are independent of data, and you just store them separately. So it's not actually compression because you're storing too many things compared to your original parameters, but it's compression in the sense of learning, because the only thing that relates to the data is parameters, which is like k. So if k is large enough, you're going to have good compression. And now I have good compression. I can show that this noise is not going to be large, and this property of the network is going to allow this noise to disappear, and everything's good. Except this, okay, so if I can measure this on an actual network, but it's not going to be helpful enough because I cannot design optimization algorithm that use this property, or I cannot use this intuition to design better models. So what I should do is that I should understand why networks are resilient to this type of noise. What property of the network trained on real data makes it sort of make this redundancy error correcting? What is that property? So we looked at networks and we tried to understand. The good thing about deep learning is that whatever hypothesis you have, you can just implement it and look at different components on the network and see what happens. And we came up with 4 different properties that we need all of them to show that the network is resilient with respect to this noise. I'm going to just briefly explain each one of them. One we call layer cushion, which is just showing that one layer is resilient with respect to noise. So if you just consider a linear function, you can just think of this as one layer of the network or just a linear function. So when can I say that if I have a noise, the ratio of signal to noise is going to be high? So that's what I want, right? I want to show that the ratio of signal to noise is going to be high. So when does this happen? You can actually show that. So if you have Gaussian noise, the way to show that the signal to noise is high is if this matrix is aligned to data. If the eigen directions of the matrix are the same direction as data, then you can observe that if you inject Gaussian noise, then because the noise is not going to be aligned with the matrix and the data is aligned with matrix, so signal to noise is going to be high. And you can capture this by just looking at the norm of matrix times input divided by norm of matrix times norm of input. Okay? So this we take this as layer cushion. So this is just for a linear case and for a single layer.
But you have a noise that is generated by this compression.
Yes.
So it's far from Gaussian.
Yeah, we have to prove, we have proofs that like it captures, so the proof, so I'm simplifying things, this is for Gaussian, but then you can show that more general noises that are Gaussian-like have the same property, and we prove that the noise resulted from the algorithm has this property. So we actually show that this is enough to this is enough to.
Compression algorithm in some sense generates noise.
Yeah. So yeah, you get with high probability that this signal to noise ratio is going to be small. So I'm explaining things in terms of Gaussian, but we define things for Gaussian, but in the proof we are not using Gaussian anymore. Now, if you have multiple layer, now it's not linear anymore. So how can we discuss this for multiple layers? What I can do is that since my function, as I explained, is piecewise linear, I can think of this as a linear function. I can approximate it by a linear function at this point, right? At any point, I can approximate it by a linear function. And the way to approximate it is just to calculate the Jacobian of the function with respect to the input. And the function, at this point, it's not even approximation. It's exactly the Jacobian times the data. And when you get far, it becomes approximation. And how bad it is depends on how far you are from the current point. So if I just approximate things with linear, I'm essentially reducing this nonlinear part to the linear setting that I described before. So I can just measure how much it's resilient by looking at the norm of Jacobian times data divided by norm of Jacobian norm of data, right? But of course, this is not right to say that like you can approximate everything with linear and everything is going to be fine. So of course, we need the property that the network, when you add noise, the network is not far from linear, right? Which we call it interlayer smoothness, which says for this type of noise, if you add noise to the data, you can actually bound the distance from the linear approximation and the actual value of the network by the magnitude of the noise. Okay, and this is actually observed on data. So this is.
If this was true, why would you need many layers? I mean, if the network, no matter how deep, stays close to linear, why?
It doesn't stay close to linear. It stays close to linear when you add a certain type of noise, and when the magnitude is not too large. So it's like this piecewise linear somehow captures this. So when you get too large, the approximation becomes bad. And also, if the noise is adversarial, the approximation is not as good. But if the noise is Gaussian or Gaussian-like, then the approximation, then it almost approximates with linear.
So for the
and
noise
this is
that you generate using the compression, it seems like it remains linear with respect to this noise.
Yeah, which is surprising.
This is a property of the final network, right?
Yes.
But in the middle, yeah, it seems like having many layers is important for training. It's not really important for.
Yeah, so it's interesting that so it's kind of, I don't know, it's interesting that you're using nonlinearity to fit data better, but at the end of the day, it actually doesn't have much of nonlinearity locally. Locally, it's linear, but globally, it's nonlinear. And the last property is activation contraction, and this is also something that people observe in practice. If you talk to practitioners, they say that the norm of data before the activation functions, which is ReLU, is not very different from norm of data after that. That's because data is roughly well distributed, and half of the activations are active, half of them are inactive. So this is actually a really small constant, roughly like 2 or something like that. So this is the third property that we need. And so what we also do is that we are measuring all these properties on networks, on the initial network and on the final network. And then so among all these properties, the one that actually seems so 3 of them seems to be just controlling the noise, and one of them is somehow responding to capacity, which means it captures capacity. So if you compare the layer cushion, which was the first property, it seems very different on random networks compared to trained networks. On random networks, it's really low. It means that the matrix, the weight matrix is not aligned with data because it's random, of course. But on trained networks, it's really aligned to data. So this is the final bound we come up with. The capacity corresponds to depth times activation contraction divided by layer cushion times interlayer cushion. So if you remember, I showed that layer cushion is not really low on trained networks, and it's very low on random networks. So this shows that the capacity is not really high. And you don't see that effect of product of layers. Everything is linear. So now, if we measure this on the same network with 19 layers, you see that it's roughly same as number of parameters. In all of these, by the way, we have ignored all the constants, log factors, depth factors, because we just wanted to see the norms. If you take those into account, it's going to be a little bit higher or lower because this is like a logarithmic plot. So we cannot claim that it's better than number of parameters because we have ignored those. So it could be a little bit higher the number of parameters if you consider all the log factors and constants. So now we have to also show that it correlates with generalization, right? Otherwise it's pointless. If you have a tight bound that doesn't correlate with generalization in practice, it's pointless. So this experiment is showing this layer cushion and contraction. Again, I think layer cushion is the main thing, trained on real labels and trained on random labels. So one experiment, you train these networks on real data. Another one, you train it on the same input but random labels. So if you have random labels, the capacity of network should be really high for those labels, right? And we actually observed that the layer cushion is higher for network trained on real labels compared to random labels. Another interesting observation is that we actually empirically observed that SGD is implicitly biasing the solution toward solutions with lower measure, like based on our measure. So these networks are during optimization, all of them have zero training error, but they are improving in generalization error. This is rescaled plots, of course it's not that close, but just to show that it's moving in the right direction. So these networks are generalizing better than these ones, and our measure is also showing that. Okay, so I think we discussed a little bit about that the real data and local search has central role on generalization, and you have to care more about them, even though it gets messy when you look at these things. We talked about some of the challenges of generalization, and then we looked at generalization via compression. We showed that you can actually find properties of networks trained on real data that allow noise stability, and then it gives you generalization bounds that's stronger than previous ones. We still have a long way to capture the actual properties we care about, but this was some improvement. Thank you.